We're going to work with section 4.5, which is a change of variable, or often known as U-Substitution. And you can see right here the definition. If you read over that, then capital F is the antiderivative of F. Then we have this, statement right here. And we can use, let U be G of X and du be G prime of X. Then we can figure out what the antiderivative of this is when we have, if you talk about it like we do in class, when you have stuff or U that you have to deal with. So with this, the role of substitution in the integration process is kind of comparable to the role of the chain rule in differentiation. So we're going to kind of see how that works when we work through a couple of these examples. To start this, I set you up with some guidelines. Decide on a reasonable substitution for U, calculate du dx, using the previous two, rewrite the integral in a form using U. So that basically we want to rewrite it in a form that was in 4.1, which is just basic integration rules. So we want to be able to use those rules. If necessary, add a constant factor to the integrand and compensate by multiplying the integral by 1 over that factor, and you'll see that play out in just a minute when we get to the examples. But evaluate the integral and replace U. So we're going to work on a couple examples. With this in mind, if you look back up here, this is the outside function, G of X is the inside function, and this is just the derivative of that G of X function. So keep that in mind. When we come down here to work these first ones, let me get a timer going. Then we're going to have, you can see it's much more complicated than the ones that we've had before. So the first thing we're going to do is we want to be able to write this. We see that this exponent, so we want to use U-substitution. So the more you do this, the better you'll get at choosing your U. But we're going to choose this term to be U. And we'll say, let's let U equals x squared plus 5x. And that's just because I want to be able to rewrite this as U to the 7th, because that's the one that has the exponent. So determine U, write it down, and the next thing is to decide what is the derivative of U. Well, we've just spent calculus 1 doing that, so this is 2x plus 5 dx. So now we have our U and our du, and we want to be able to rewrite this integral over here. So we're going to have U in terms of U. So U to the 7th du. Now when we do that, in the rewrite step, you want to make sure that you're not changing the value of the problem. We're just rewriting it in a different term so that we can use an integration rule from previous. Now, U to the 7th would be, if this is U, this is U to the 7th, so that's accounted for. Now the next thing we have, this 2x plus 5 dx is the 2x plus 5 dx is the du. So we can see that everything is there and everything's accounted for. We're just using terms of U, variable U. So now we can just go ahead and integrate using our rules. Remember, this is U to the n plus 1 over n plus 1, and then we have to remember plus a constant. Now we can stop right there, or we can replace U with this value. That's just going to be U to the 8th divided by 8 plus a constant, and plug in U. So U is x squared plus 5x. Okay, so that's a very basic one. Let's move to the next one. Alright, so the first thing is try to determine a U, and like I said, the more of these you do, the better you get at that, which this one's pretty obvious what U is going to be. U is going to be this, so we'll say U is equal to 3 minus x. Then you always calculate the derivative of U, which is du. In this case, it's just going to be negative 1 dx. Next step is to rewrite this in terms of U, so that's going to be U to the 10th du. And then now we need to just make sure that everything's accounted for. So u is there, so that's u to the 10th, so u to the 10th is there. And then du is -1 dx. Well, the dx is there, but what's extra? If we see that -1 is extra, so we have to account for it, so pull it out front. So also the reciprocal of that is 1/1, so we just pull that out front. And then now we're ready to integrate. Use some regular integration rules. So u to the n plus 1 over n plus 1 plus a constant, and then of course we had that -1 out front, or you can just keep the negative. If you replace u, then we would have, let's see, 3 minus x to the 11th power divided by 11 with the negative out front plus a constant. Okay. This next one, just like we did before, anytime that we can rewrite, we would like to rewrite this problem so that we can see it as 3x plus 2 to the what power? Good. To the 1/2 power. Now when we're looking at it, it makes it a little bit easier for us to determine u. So u is going to be 3x plus 2. We calculate du, which is just going to be 3 dx. And then now we want to come over here and rewrite this in terms of u. So that would be u to the 1/2 du. Let's check and make sure everything's there. We have u to the 1/2 is this. And du is, there's a 3 dx here and there's just dx. So what's extra? The 3, and we want to account for that, so we do the reciprocal of it, so we pull out a 1/3, because then the 1/3 would cancel with the 3 and we would just be left with dx. Where up here we had a -1, but as a fraction the reciprocal of that is still -1, so it was a little bit harder to see that in the previous example, but you want to account for that 3 so that way they would simplify. And then now we're ready to integrate. And we would just have the 1/3 out front, and then we have u to the n plus 1 over n plus 1, which would just be 2 over 3 plus a constant. And then you can simplify that. 2/9 u to the 3/2 power plus a constant, and if you replaced u with the 3x plus 2, you would get 2/9 and then 3x plus 2 to the 3/2 power plus a constant.